Dear students, in the last 3 video lectures we have discussed over Otto and diesel cycle, but in this video lecture we will discuss on Brayton cycle. Brayton cycle is also one type of gas power cycle. It is mostly used in gas turbine power plant. So before starting this cycle we have to know what are the components of this particular cycle. So mainly there are 4 components of this cycle, that is 2 heat exchanger here and here, 1 compressor and another is turbine. So there are 4 parts of this particular cycle. Now like Otto and diesel cycle, this cycle also has 4 steps. So this cycle also have 4 steps. Number 1 steps from 1 to 2 is isentropic compression. Number 2 to 3 is constant pressure heat addition. So in this step heat is added or fuel is injected into the gas turbine power plant. Now 3 to 4 is the isentropic expansion. So it is isentropic expansion. In this case it is occurred on the turbine. So this is the power output stroke. And 4 to 1 is the heat rejection stroke but in constant pressure. 4 to 1 is the heat rejection stroke but in constant pressure. So like Otto and diesel cycle, this cycle also has 4 strokes. So let's see, 1 to 2 is the isentropic compression, 2 to 3 is the constant pressure heat addition, 3 to 4 is the isentropic expansion, 4 to 1 is the constant pressure heat rejection. So here PV and TS diagram is given. PV and TS diagram is given. You just have to understand these two diagrams. Now you have to derive the efficiency of that particular cycle. So Q1 is the heat input in 2-3 process. So for mkg of air, Q1 is equal to mCp T3 minus T2. Cp is the specific heat at constant pressure. And now Q2 is the mCp T4 minus T1. This is the heat rejected from that particular system. This heat is rejected from this portion, 4 to 1 portion. Now efficiency of that particular cycle is equal to 1 minus Q2 by Q1. Now if we replace Q2 and Q1, then the equation become 1 minus T4 minus T1 by T3 by minus T2. Again we can write T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma from the adiabatic law of compression or expansion. And also we can write it equal to the T3 by T4 because P2 is equal to P3 and P4 is equal to P1. It is clearly shown in the diagram. P2 is equal to P3 and P1 is equal to P4. Now you can write T minus 1 is equal to T3 minus T2 minus 1 from that above equation. Now you can also write T4 minus T1 by T3 minus T2 is equal to T1 by T2 is equal to P1 by P2 whole to the power gamma minus 1 by gamma is equal to P1 by V2 by V1 whole to the power gamma minus 1. You can write by the law of adiabatic expansion or compression. Now you know that RK is the compression ratio is equal to V1 by V2. So the efficiency becomes 1 minus V2 by V1 whole to the power gamma minus 1. Now if you replace it by RK is the compression ratio, then this equation become this. So this is the efficiency of Brayton cycle. Now if you introduce another term, that is pressure ratio. Pressure ratio is the ratio of P2 by P1. So if we replace the pressure ratio by compression ratio, then the equation becomes this. So this is one type of one form of that particular efficiency equation of Brayton cycle. So this is also the efficiency of Brayton cycle in terms of pressure ratio. Now some notes are there. Number one is the efficiency of Brayton cycle. It totally depends, or it is a function of RK and RP. So RK is what? RK is the compression ratio, RP is the pressure ratio. And number two, for the same compression ratio, efficiency of Otto cycle is equal to efficiency of Brayton cycle. So this is for all. In the next class, we will solve one numerical problem of this particular chapter. Thank you.